Hello, this is Nick Andre welcoming you to another screencast. In this screencast, we will study Layer 4 of the OSI model and learn the role that both UDP and TCP have in the communication process. Explore the means in which segments or datagrams transfer messages between client-server applications using both reliable and unreliable methods. On other screencasts, I discussed what elements make up a network and how they are used to send messages. We explored the OSI model encapsulation process and discovered the relationship clients' applications have with server daemons. We will be focusing our attention on the transport layer. The transport layer is the first time data is encapsulated and also the time when it is segmented. As a result, this layer is responsible for regulating the flow of information from source to destination reliably and accurately. To ensure a message and all the pieces that make up this message is delivered error-free and in the same order as it was sent, the transport layer relies on TCP. Once all the pieces arrive at the end device, TCP, or Transmission Control Protocol, will reassemble the segments back into data and pass it up the stack, thus keeping the applications unaware how data gets to end devices and lower layers from knowing of multiple applications. To maintain multiple communication streams between applications or services running on the same machine, the transport layer adds port addresses to each segment header. A dynamic port address is placed in the source field of the segment header on the client side. This address is used by the operating system to identify the communicating app. These addresses, both source and destination, will allow receiving host to forward the data to the appropriate application. By associating well-known applications with a default port address and using applications like Wireshark, network administrators are able to determine types of conversations by the pieces of data flowing between a client and server. TCP and UDP-based services keep track of the various applications that are communicating by using these port addresses. This is about the only thing TCP and UDP have in common. Unlike TCP, UDP is said to be unreliable. That is because its header contains only the fields required for keeping track of apps. This low overhead allows UDP to deliver data faster and as it arrives. Since it doesn't establish a session with another end device, it is also unable to resend lost data. Programmers choose the appropriate transport layer protocol based on the nature of their application. That is to say, a programmer is left to decide whether the data feeding their application is time-sensitive or content-sensitive. Let's use a telephone conversation as an example to illustrate how data can be time-sensitive more so than content-sensitive. Imagine in this conversation your friend is telling you who they plan on voting for in the upcoming election. Using TCP, the programmer is ensured that their user's message will arrive. Great. Now you know that your friend is voting for Heisenberg. But when will you get this message? Before or after the election? It all depends on the quality of your connection with your friend. If this connection is poor, then TCP could be resending the same message over and over until it receives an acknowledgement from your computer. Remember, it guarantees delivery, but it does not use it in a timely manner. Hence, the need for a protocol that provides basic functions for efficient delivery that is on-demand or transaction-based. Let's treat the same conversation as a series of transactions. We typically call these a dialogue. You say something, they respond. When you begin your conversation, you don't check to see if your friend is there. You simply begin to talk. As you are talking, UDP is shipping your words to your friend. Since UDP cannot guarantee delivery, it is up to your friend to ask for any of the missing pieces. Who are you voting for again? I couldn't hear you. UDP gets the message there as fast as possible, avoiding the hang-up due to the dead silence caused by TCP. As a connection between clients become poor, the more each user will ask the other to say it over again. Hence the cliche, "Can you hear me now?" Notice I mentioned that you began your conversation without checking to see if your friend is on the other end. Your conversation begins the moment you pick up the phone and dial their number. Unaware of your friend's availability, You just dial their number. This is the same approach UDP follows. Unlike a TCP session, UDP is connectionless. They assume someone is out there to answer the phone and will do their best to get the data to them. As a result, the only fields in a UDP header are the source port, destination port, length, and checksum, and they are used to track the applications, not their datagram. A connection-oriented protocol like TCP creates a session before transmitting data. During the session connection process, both end devices synchronize their sequence and acknowledgement numbers. These numbers help TCP to ensure same order and dependable delivery. As you will see on other slides, they will also give TCP the ability to control the flow of data. Please note, the sequence and acknowledgement number fields are 32 bits, as I might have said they were 16 bits on a previous video. I do apologize for any confusion this may have caused. The important thing, however, is a TCP header consists of 12 more bytes than a UDP header. That is 12 more bytes per each segment that leaves the transport layer. This can add up really fast during a long conversation. The header of each segment, or datagram, contains a source and destination port. The source port number is the number for this communication associated with the originating application on the local host. The destination port number is the number for this communication associated with the destination application on the remote host. Port numbers are assigned in various ways, depending on whether the message is a request or a response. While server processes have static port numbers assigned to them, clients dynamically choose a port number for each conversation, between 49,152 up to 65,535. Port numbers are used to identify the application having the conversation. They cannot be used to identify the end devices that are running these applications. To identify an end device, a network administrator would use a network layer addressing protocol like IP. A socket is simply an IP address, a colon, and a port address glued together. In this example, a client communicating to a local web server would open socket 192.168.1.20:80 if the server IP address is 192.168.1.20. By combining TCP with IP, a simple web request/response are able to traverse the complex world of interconnected devices without data loss. Once the segment arrives at the receiver, the operating system can use the destination port address to identify the anticipating service. Consequently, two or more services running on the same server cannot be assigned the same port number. Just like two or more devices on the same network cannot have the same IP address, two or more services cannot have the same socket. This would cause the operating system to misplace data. To organize this madness, the Internet Assigned Numbers Authority was created. They took the total port range from 0 to 65,535 and divided it up into three parts: well-known, registered, and dynamic. Well-known ports are typically used to respond to open services like DNS, HTTP, SMTP, FTP, Telnet, and etc. Where on the other hand, registered ports are typically used by proprietary applications like Kazaa, which uses port 1214. And dynamic ports are assigned to client apps when initiating a connection and stored in the source port field of a segment or datagram header. Here are just a few well-known ports we started to explore in the previous screencasts that are managed by the IANA. Notice the transport layer protocol used by each well-known application, in particular DNS using both TCP and UDP. DNS primarily uses UDP to serve requests. The transmission control protocol, TCP, is used when the response data size exceeds 512 bytes or for tasks such as zone transfers. Earlier we discussed that the application layer passes data down to the transport layer, and it is here where the encapsulation truly begins. The transport layer breaks the data up into tinier pieces called segments or datagrams. As discussed in a previous screencast, this is to prevent network congestion. Network congestion is avoided because smaller pieces have a higher likelihood of arriving undamaged. If these pieces arrive without a problem, then the sender can keep sending new pieces until the file is transferred, hence minimizing redundant packets that add to network congestion. The size of a segment can vary from connection to connection, and it depends on the maximum transmission unit of each medium along the way. To help you visually, the transport layer divides data into pieces and add a header for each piece to be delivered over the network. Applications that are time sensitive would be encapsulating using UDP. These headers would include only a source and destination port. Data-sensitive apps that need dependable delivery methods would be encapsulated with a header that consists of source and destination ports. Sequencing for same-order delivery, acknowledgments of received segments, and flow control/congestion management. Interleaving these smaller pieces from different communications is called multiplexing. Multiplexing allows for more efficient use of a connection's bandwidth and quote-unquote equal treatment of each application's growing need for a network connection. Thus, by breaking application data into segments and multiplexing these segments help to prevent any client or application from consuming all the bandwidth. Interconnected networks such as the Internet often provide multiple pathways to the same destination. The different transmission times of each pathway can cause data to be scrambled. Sequence numbers found in the TCP segment header allow receiving hosts to reorder each segment of the data and reassemble them back into their original form. In this case, our sender has 6 segments shipping out to another device across multiple networks. The left column of the segments under the receiver shows the actual order in which the segments arrived. The right column illustrates how the transport layer, using sequence numbers, reorder the segments back to the original arrangement. The 3 basic operations of reliability are as follows: the ability of tracking transmitted data, acknowledging received data, and retransmitting any unacknowledged data. To track data, TCP must first establish a connection-oriented session. This session creates 2 one-way streams, an upload stream from the client to server, and a download stream from server to client. Each stream is used to send data along with acknowledgments. Using numbering and sequencing, a host is able to detect missing acknowledgments and retransmit accordingly. To prevent a host from being overwhelmed with segments, TCP implements a technique known as flow control. We will discuss flow control on another screencast. Unlike TCP, UDP diagrams are lean and as a result are unable to keep order. Out-of-order diagrams are reordered and any lost datagrams are not resent. As before, our sender has 6 datagrams shipping out. Unfortunately, datagram 3 is lost its way to the receiver. Since UDP doesn't contain any sequence numbers, the receiver has no way of knowing what's missing. Any application that uses UDP must either implement a control system to keep track of the pieces or accept the order in which data comes in. To better understand this, let's take a closer look at online video services like Hulu or Netflix. Most video services are time sensitive and thus prefer to use UDP. Unfortunately, datagrams can arrive out of order. That is to say, the end of the movie could arrive before the beginning of the movie. To prevent the user from seeing the movie out of order, the application developer had to build their app with control mechanisms that keep track of datagrams. Why would a developer go to so much trouble when TCP offers same-order delivery? TCP is too slow and has way too much overhead to handle video services. Case in point, a movie typically consists of 24 to 30 frames per second. If one single frame every second was dropped, the average user would not even notice. Fortunately, UDP would keep humming along. UDP is able to do this because it does not keep track of the datagrams. Remember, UDP does not establish a connection. with the other end device. Once a frame is ready to be shipped, it is sent, processed, and displayed on the other device, thereby minimizing delays in data delivery. TCP, on the other hand, would require a connection first and complete transmission of the movie before it is passed up the application layer. To summarize and simplify Chapter 4 OSI Transport Layer screencast, UDP and TCP can be compared to streaming a movie versus downloading a movie. One allows you to watch it as it comes in. The other requires the entire movie to be downloaded before watching. In this screencast, we explore the role that both UDP and TCP have in the communication process, explore the means in which segments or datagrams transfer messages between clients/server applications using both reliable and unreliable methods. In the next screencast, we will explore how TCP delivers data. Until then, take care of one another.